there is one more major variation in surface wind that we need to consider. This is the change from day to night. In other words, the diurnal variation of the surface winds. Let's look at the situation during the day. In the diagram shown here, we can see thermal heating is causing more mixing and turbulence. Notice that the mixing is causing the faster winds to interact with the slower surface wind. This will cause the surface wind to be stronger and gustier than usual. This effect is maximised at about 1500 hours, when we have maximum surface temperatures. So at approximately 1500 hours, we would expect the fastest and gustiest surface winds. The situation at night is very different. At night, there are no thermal currents, and therefore little mixing when compared to the daytime. Therefore, the surface wind speed remains low, since there is little interaction with the faster winds above. This effect will be most apparent when the Earth's surface is at its coldest, which is just after sunrise, approximately 0600 hours. Let's now use what we have just learnt and see how the direction and speed of the surface wind will change diurnally. The example shown is for the northern hemisphere. Again, like before, we will use the geostrophic wind and its forces to understand what is happening. At approximately 1500 hours, we said the surface wind speed will be at its highest. Therefore, the Coriolis force will only be slightly reduced compared to the geostrophic wind. But at 0600 hours, the surface wind is at its slowest, and the reduction in the Coriolis force is much greater. Therefore, the surface wind will be deflected by a greater amount from the geostrophic. The surface winds will simply move between these two extremes depending on the time of day. From 0600 onwards, the surface wind will increase in strength and move towards the 1500 position. But after 1500 hours, the wind will slowly return and move towards the 0600 position. The southern hemisphere images can be seen if you click on the button. This completes the theoretical analysis of the surface wind and geostrophic wind. Remember, we considered the geostrophic wind and its forces in order to better understand what is happening at the surface. If we now take a surface pressure chart like the one shown here, we can see some parallel isobars and therefore find a geostrophic wind. Remember, the direction is found by using Bayes-Ballott's law. If this is a northern hemisphere map, the geostrophic wind will be blowing from the west at about 285 degrees. The speed can be found from the geostrophic wind scale. In this example, it is 20 knots. What will the surface wind be doing though? If this location were from the sea surface, we would have to remember what direction the surface wind was in relation to the geostrophic wind. In the northern hemisphere, the surface wind was like this compared to the geostrophic. If you remember, the angular difference was 10 degrees over the sea. Therefore, the surface wind is approximately 275 degrees and the speed is about 70% of the geostrophic, therefore approximately 14 knots. It is important to note that surface winds, and in fact any wind within the friction layer, blow slightly across the isobars towards low pressures, just as we have seen in our example.